Okay, and of course the rest of the semester we're doing trig. We're going to be working on that and kind of doing an overview of everything in the trigonometry. Oops, I don't have anything put up today. There we go. Okay, so what we're going to do on this is we're going to look at just kind of wrapping up what we're talking about with angles, and that's a big deal in trigonometry because we'll always be talking about angles. So a couple of things we're going to do is, this is in radians, okay? Unless I put the degree symbol, then you assume you're in radians, okay? It's not because there's a pi there, it's because there's not a degree symbol. So this is a radian measure. The key thing that you want to remember is pi radians is equal to 180 degrees. So you want to know that. So what I'm going to do on this problem, first of all, before I sketch the angle, is I'm just going to use my calculator and I'm going to convert this to degrees, because to me it's easier to draw a sketch if it's in degrees. So what you want to do is just replace the pi with 180. And I'll just take my calculator and estimate this anyway. So I'm going to do negative 12 times 180 divided by 7. It'll come out with a decimal result here, but that's okay because we're just sketching anyway. So that would be the same thing as about negative 308.6 degrees. Okay, so we're going to do that. Now, when we do a sketch of an angle, there's a couple things that you want to know how to do. First of all, when you do a sketch, you want to just draw like XY axis, and you do this. And what we're doing is we're doing this in what we call standard position. And when you're sketching an angle in standard position, you always want to highlight the x-axis. And then there's things you want to remember. What is negative? If the angle's negative, what did we talk about with that? That meant what? Go clockwise, right? Okay, so you go clockwise this way around the circle, okay? And then you just kind of count it out. Like if you go from there to there, that's negative 90. If you go halfway around the circle, that's negative 180. And then negative 270, all the way around the circle's negative 360. So you estimate on this. So what you're really doing is you know that 308 is somewhere between 270 and 360. So you estimate where it is. It doesn't have to be perfect. And then you do that. Now you need to have, for a graph, you always need to have these things. You need to make sure that you have the rays. Okay, you always start at the x-axis. And then the terminating ray, and the other thing you want to always have is that arrow to show the direction, whether it's clockwise or counterclockwise, okay? So that's it. Okay, so the quadrant I'm in, remember the quadrants go like this, so the quadrants we talked about go 1, 2, 3, 4, so that means that this angle is in quadrant 1. Okay, that's it. Okay, it's negative, so it ends up terminating in quadrant 1. Okay, is everybody with me there? Okay. All right. So if you're sketching an angle, we worked on that a lot last time, and if it's in radians, it's just as easy to convert it to degrees, and you're just estimating where that falls and what quadrant that's in. Okay. Now, the other thing we're going to talk about is kind of review is coterminal angles. Coterminal angles are always off by 360 degrees. So 360 degrees is the same thing as 2 pi radians. Okay, you want to remember these two things. 180 degrees is pi radians, so therefore 2 pi is 360. So you want to remember that. So if we're going to find an angle that's coterminal to that, all that means is it's going to terminate at the same place. Okay, it may go another lap around the circle, or it may go in a different direction. Doesn't matter. So since I gave you a negative angle, what we're going to do to find a positive coterminal angle is we're just going to add 2 pi to it. Okay, there's no need, you don't want to add 360 to it because I want the answer to be in radians anyway. Okay, so I put that over 1. I get a common denominator, so you want to just change that to 7 over 7 like that. And then that would just be negative 12 pi over 7 plus 14 pi over 7. So that's equal to 2 pi over 7. Okay, so that would be your angle that's coterminal to that. We ended up with a positive answer, so that's it. Okay. If we want to find an angle, another negative angle that's coterminal of that, well, we would just do this. Okay, we just subtract 2 pi. Because if we do that, you're just going to get another negative answer anyway. Okay, so I'm going to do the same thing here. And I'm going to get the common denominator of 7 again. So what I would have here then is this would be negative 12 pi over 7 minus 14 pi over 7. So the answer to that problem would then be negative, 26 over 7 is what that is. Okay, so that's it. Whenever you're finding angles that are coterminal, there's nothing to it. You either add 2 pi or subtract 2 pi. If it's in degrees, you add 360 or subtract 360. That's it. Everybody with me there okay? Okay. So coterminal doesn't mean the angles are equal. It just means they start at the same place and they end at the same place, but they have a different number of laps around the circle. That's all that means. Okay. All right. Next couple of things I want to talk about is a subtended arc of a circle. Talk about what that is and where the formula comes from. So one thing that you're going to get familiar with is we have a formula S equals R theta. If you have a circle, S is an arc. We call that the subtended arc. Theta is a central angle. This is the center of the circle right there, and then R is the radius in that formula. So I'm going to show you where that formula comes from. You have to know a little bit of background information to do this. And so what we're going to do is we're going to put together this proportion. So we're going to relate the part to the whole. The part is the portion around the circle. The whole is all the way around the circle. So we're going to do this. When we put this together, we're going to do, first of all, the arc length. And the arc length is S. Okay, so we're going to use S in place of that arc length. And then we have the circumference. So we're going to relate that to all the way around the circle. You guys from your background remember what the formula for a circumference of a circle is? 2 pi r, very good. Okay, so we're going to put 2 pi r there. Okay, make a note of that if you need to. The circumference of a circle is 2 pi r. So again, the point of this is, when we're doing this proportion, it's just we're relating the part, S, to the whole 2 pi r. Okay, and then when we go to this next side of this, we just do this. Now we do the angle in radians. Well, that angle is theta. Okay, and then we relate that to 2 pi. Why 2 pi? Because 2 pi is all the way around the circle, right? So what I want you to understand by this is we're relating S is the part, 2 pi r is the whole, theta is the part, 2 pi is the whole. Does that make sense to everybody? Okay, so part to whole proportion, and then we can cross multiply and solve this. So what I'm going to do is actually just multiply both sides of this equation by 2 pi r, and then out will pop the formula. Okay, so I'm multiplying by 2 pi r on both sides of the equation. All right, and when you do that, you're going to find enough cancellation. You should get S equals R theta, because this will cancel. And then on this side, the 2 pi's cancel. So what you're left with is S equals theta times R. We usually write that as S equals R theta. Okay, so that's how you come up with that formula. That's how you can find a length of an arc in a circle, is by multiplying the radius by the radian measure of the angle. Okay, so you have the formula S is R theta, and then the key thing, and this is real important, is the measure of the central angle must be in radians, because if it isn't, you'll get answers that are ridiculous. I mean, totally ridiculous. It won't make any sense at all. So you have to, this is an example of why we got to have radian measure. Okay, degrees won't do you any good if you're finding the arc length of a circle. Okay, any questions about what I did there? Okay, this formula is real easy to work with, but I'd like to kind of give you a sense of where that comes from. So I'm just going to do a couple of examples on that. So first of all, on this example A here, we're going to find the length of the arc. So what we're looking at is we're just looking at this piece right here, and we're going to use S. S is the variable we generally use for that. So we're going to use S equals R theta. So the radius is 12, theta is 45. Now I'm going to do something wrong on purpose. I always like to do this, and a lot of times students, when they're doing the homework, they never catch this. But what we do is we do S is equal to R theta. So if I did 12 times 45, what is that? It's too big, I can tell you that much. So that would give you 540. I'm just going to ask you a simple question. Don't you think that that's a tad bit big? If that radius is 12, there's no way that little piece of the circle is 540. See, that's nonsense. So what you have to do is you have to convert this to radians. Okay, you don't want to do that unless theta is in radians. Okay, so we learned about this earlier. This would be before spring break. The way that you change a degree to radians is you multiply by pi over 180. Okay, so you do that. Okay, and then you can reduce the fraction if you want to, or you actually probably don't have to in this problem because we're going to probably use our calculator anyway. Okay, well, actually 45 divides evenly into 180. So I'm just going to reduce the fraction. So 45 over 45 would be just the numerator's pi. 180 divided by 45 is 4. So pi over 4 is the same thing as 45 degrees. Now we're going to get a much more sensible answer to that problem. So if you want, what you always want to do is make sure that your angle is in radians. If it isn't, then you got to convert it. Okay. Now to finish up, then we'll do this. Okay. So now we have S equals r theta. The radius is 12 in this problem. The angle is pi over 4. Okay, now you can go through and reduce that. If you multiply straight across, you get 12 pi over 4, which is 3 pi. Well, I'm going to take my calculator because I want to kind of make sense of this problem with a decimal. So if I just do 3 times pi, using my pi key on the calculator, I get about 9.4. Okay, which to me, what do you guys think? Is that a little more logical than 540? Yeah, okay. I say a lot of times students don't ever catch stuff like that when they're doing their homework or doing a test. I mean, you want to think about, you know, what's reasonable to you. That's the arc length is approximately 9.4. That's it, okay? All right, so S equals r theta is the formula you use. Just make sure that theta is in radians, okay? That's the whole key. All right, this one we're going to do the same thing. This time I gave you the radius. I gave you theta. Is theta that I gave you 3 pi over 5, is that degrees or radians? Which is it? Radians. There is no degree symbol, so that's in radians. So that means in this problem, all we got to do is just do r theta, and we'll use our calculator on this. So we have 15.5 centimeters for the radius, and then we just do 3 pi over 5. And then you can put this in your calculator in one step, and then we'll just round this off. Okay, so I'm going to go 15.5, and then times 3 pi divided by 5, and that should give a fairly logical answer. So that's going to be approximately 29.2 centimeters would be the length of that arc. Okay, that's it. Okay. All right, so that's it. You won't have any trouble with this as long as you understand that the theta has got to be in radians. All right, everybody with me okay so far? Okay, S equals r theta. Okay, the other thing we're going to look at is area of a sector, kind of talk about what that is. This is just another thing to show students it's an application of angles and the idea of why we got to have radian measure. So what we're going to get on this is we're going to develop a formula. Now a sector is just a piece of the circle. Again, this is the center of the circle, and then that's the arc length S, and then that's the radius, and then that angle there we're going to say that's theta. Okay, so we already know S equals r theta, but we want to find the area of that sector. Think of that like a piece of pie or pizza or something like that. That's a sector. So actually what we do is we do a part to whole proportion. So what we're going to do is we're going to fill this in kind of like this and derive this. So area of sector, let's just write A for area for that part. Okay. And then in the bottom, what's the area of an entire circle? What's the formula for area of a circle? You know that? It's not 2 pi r, but it does have pi in it. Anybody remember that? Pi r squared, right. Okay, so that is pi r squared, like that. Okay, so you're relating the part to the whole. Okay, and then what we have is the arc length of the sector. Well, the arc length of the sector was S equals r theta. Okay, so I'm going to put r theta there. That's the formula that we just developed. And then what is the circumference of a circle? That was 2 pi r. Okay, so again, if we put this together, we should be able to, a formula will pop out of that if we do that. So the idea is, this is the area related to the area of the circle. That's the arc length related to the circumference. Does that make sense? Part the whole? Okay. Now, what you need to do on this problem is just multiply both sides by pi r squared, and out will pop the formula that we're looking for. Okay, so that's going to cancel that stuff out. That's going to give a here. If you go over to this side, it looks like the pi's cross out, and one of the r's crosses out. So that r squared over r just gives you an r left over. So what you're left with is r theta, and then you have an r, and then you have a 2. So what it is it's r squared theta over 2. Okay, or you can write it this way. Most of the time a textbook writes the formula as 1/2 r squared theta. Okay, that's the formula for an area of a sector. Okay, does that make sense how I figured that out? You know, proportions are very helpful. We use that to figure out formulas all the time on stuff. So again, a couple of things. I mentioned this already, but the area of a circle is pi r squared, and the circumference is 2 pi r. So the area of the sector is 1/2 r squared theta, and again, theta is in radians. If it's not in radians, your answers won't make any sense. Okay, so that's real important. Okay, all right, so we're going to just crunch a couple of these things out. And on this example here, we're going to find the area of this sector. You've got everything you need to know. All you got to know is 2 things. You got to know the radius and the angle. Okay, what's the first thing you got to do with that 100 degrees? Change to radians. Okay, otherwise you're going to get ridiculous answers. Okay, so step 1, theta is 100 degrees. So multiply that by pi over 180, okay, to get that into radians then. You can reduce the fraction, or you can bypass that because I'm going to want you to get a decimal anyway on this probably. So I'm going to just cancel out that, and that would be 10 pi over 18. Then I can divide by 2, just reducing the fraction. So that will be 5 pi over 9 radians. Okay, now sometimes on your homework, they might want the answer to be exact with pi in the answer. Sometimes they might want it to have a decimal. So I'm going to get the exact answer, and then we'll use a decimal on that too. Step 2 is we're going to find the area. So the formula is 1/2 r squared theta. So we have 1/2. The radius is 12 centimeters. That gets squared. And then theta is 5 pi over 9. So I'm going to go ahead and leave pi in the answer to begin with, and then we'll use the calculator to get a decimal. Okay, so that's going to give me 1/2. 12 to the second is 144. Notice that you have centimeters to the second, and that's what you would expect in area anyway, is have square units. That's why. Okay, then we multiply that by 5 pi over 9, and then you can reduce this fraction. Okay, and there's several ways to reduce this fraction. One thing that I know, and you can use your calculator to help, that is actually 16. So if 9 goes into 9 once, 9 goes into 144 16 times, and then what you have is 16 over 2, that's just 8. Okay, and then I've got 8, and then I still got the square centimeters times 5 pi, so that would actually give 40 pi square centimeters. And all of that work I did was reducing fractions. There's more than one way to do that, but that's what you would end up getting on that. I just reduced. You can multiply straight across and reduce at the end if you want to. That's just the way I chose to do that. Now what I'm going to do is just take the calculator and do this like this. So I'm going to do 40 times pi, and I'll just round it off to like 1 decimal, so the answer would be about 125.7 square centimeters. So either one of those answers. You want to know, being able to get an exact answer and a decimal answer. That's it. Okay? So that would be the area of that sector in square centimeters. Okay? And that's pretty logical. That makes sense to me. Okay? All right. Any questions about what I did? Okay. All right. Mainly it's just using the formula and make sure that you know how to handle the angle theta. That's it. You won't have much trouble with this. Okay, the last part of this section is sometimes can be a little bit harder for students. This is some physics applications. Still just kind of looking at angles. And what we're going to look at is angular and linear speed. And this really will help you make sense of why we have radians, why we need to understand that angles can get bigger than 360 degrees and so forth. So a couple of definitions I'm going to look at. First of all, is angular velocity just is a measurement that represents the motion of a circle as it rotates through an angle in radians over a period of time. So there's a couple of things on here. Our textbooks always use the omega equals theta over t. Omega looks like a W, and theta is the central angle, t is the amount of time. So that gives you what we call the angular velocity. So what it is it's a measurement of what angle a circle rotates through in a unit of time, okay? Your car, usually most all cars have what's called a tachometer in it, and a tachometer, what that's doing is it's measuring angular velocity. Your engine's turning, okay? There's a crank that turns the pistons and everything, and it goes real fast. The faster you go, the harder your engine works, the faster it turns. So that is an angular velocity. So a lot of times I like to tell students this as an analogy. Think of your tachometer, okay? And a tachometer, this RPM, is revolutions per minute in thousands. So if you had the tachometer up to 3, that would really be 3,000 revolutions in a minute. So that means every time a minute goes by, that crank in your engine goes 3,000 times. That's pretty fast, isn't it? Okay. That's the way things like propellers in a plane work, or go really, really fast. So they go through a much bigger angle than 360. So every time a minute goes by, if you're doing 3,000 RPMs, that angle is way bigger than 360, right? That's lots of laps. So that's one of the reasons why angles need to be bigger than 360, okay, for this type of application. Okay, a couple of things I want you to write down. The units for angular velocity generally are radians per unit of time. So most of the time what we're going to say is we'll say like radians per second maybe, and sometimes we even say like revolutions per minute. But the typical thing is radians per second, radians per minute, that kind of thing like that. And as I go through this, radians is not really a unit, it's a placeholder. And I'll kind of talk about that as we go. So it's really, the unit's weird. The unit really technically is per time. It's just a number per time. So radians is really unitless, but think of it as a placeholder and it'll help you with these problems. Okay, so that's what that is. All right. Okay, so let's look a little bit at this bottom example here. And let's see, this one says you have the edge of a Ferris wheel. It's turning at an angular velocity of 12 radians per minute. Okay, that's the type of units we'd expect from an angular velocity. Then it says, what is the angular velocity at a point 10 feet from the center? Okay, well, here's what I want you to try to understand on this problem. And I had an applet at one time that kind of helped students understand this a little bit better. But what happens is, okay, let's just say that, here's the edge of the Ferris wheel. Okay, and I don't know what that is, but this says, what is the angular velocity 10 feet from the center? Okay, I don't know how far out that it goes. Well, here's the question I want you to ask yourself. Angular velocity, we're going to think about whether that's the same or different. The idea is, remember what angular velocity is doing, it's telling you how many rotations you go through in a unit of time. Okay, so wouldn't they both go through the same angle in the same unit of time? They would have to. Think about that, okay? Like if 1 minute goes by and you make one lap around the circle, it's still going to take that, they're going to end up at the same place, right? Because if they don't, then the Ferris wheel's going to disintegrate, right? So basically my point is that everywhere on there, it's going to have the same angular velocity. Does that make sense? It rotates through the same angle in a unit of time, so it's the same. Now, We're a little bit later, we're going to learn about what we call linear velocity. So you're going to find that if you were looking at speed in miles per hour, that one is different than that. Okay, if we're talking about miles per hour, it's different. But if we're talking about an angle per unit of time, they sweep through the same angle. That's what you got to understand. So basically, you just want to make a note on this that it has the same angular velocity anywhere on that radius. Okay, so it's always going to have that. So the answer to the problem would just be 12.5 radians per minute. Everywhere on that radius of that Ferris wheel, it's going to turn through that same angular velocity. So that's the idea. Okay, all right. So let's see. This one we're going to look at is on example 2. Next page, this says the tachometer is reading 2.8 RPM. We're going to find the angular velocity in radians per second. So first of all, you always got to understand what you're given, and that's a big deal when you study physics, is units tell you what you're given. If you're given RPM, that means that you are given an angular velocity. So angular velocity is omega, so I gave you the angular velocity, okay? If I give you like radians per second, revolutions per unit of time, I'm giving you an angular velocity. So I would just start this problem by writing down omega equals 2.8 revolutions per minute. And then we're going to do a unit conversion on this, and we're just going to change this to radians per second. Okay, so it kind of depends on your background. When I was a student, I didn't learn how to do unit conversions with what we call dimensional analysis until I took chemistry. And that's kind of when they teach you the smart way to convert units, and we just kind of take things away. So here's the idea. We don't want revolutions in our answer. So if revolutions is in top, we want to come up with a connection between revolutions and radians. So that's what we're going to do. Okay, that's why I'm putting the revolutions in the bottom, so I get it to cancel out. Well, here's what the thing is, okay? What is, if you go through one revolution in a circle, how many radians is one revolution around a circle? 2 pi, good, okay? So that's 2 pi. Now, that's something you may want to write down. I mean, it's one revolution around a circle is 2 pi radians, because you'll use that unit conversion all the time, okay? Now we're in radians per minute. Okay, so now we're going to get rid of the minutes. We want the minutes to convert to seconds, so I'm going to put the minutes on top, then I'm going to put the seconds on bottom, okay, because I want to end up with radians per second, okay? Well, the conversion factor on that, of course, is 1 minute, 60 seconds. We call that a unit fraction when you have something like 1 minute over 60 seconds. Those are equivalent to each other. That's really can be thought of as 1. If you think about that, 1 minute and 60 seconds are the same quantity, therefore it's 1. So we call that a unit fraction. So when we're doing conversions this way, we're multiplying by unit fractions. So now we're ready to just get our calculator out, and with this one, I'm just going to kind of multiply straight across to begin with, and if I do that, I'll have 2.8. and then times 2 pi, and on this one I'm just going to choose to go to the decimal route. So that'll give that, and then divide by 60, so the bottom is 60 when you multiply that out. So that would be about let's just use 2 decimals, it's about 0.29 radians per second, okay? So that's what the tachometer means, is 2.8 revolutions per minute is the same thing as 0.29 radians per second, okay? All right, and don't worry about, like on a car, technically in a car, if it says 2.8, that really means 2,800 revolutions per unit of time. Don't worry about that on that problem. That's not the point behind that, okay? So that one was basically a unit conversion problem then. All right, is everybody with me there? Okay. Okay. Try to think of the tachometer as a measurement of angular velocity. Okay, that's what that's measuring. Okay, next thing we'll look at is the idea of a linear velocity. And a linear velocity is that would be a point on the circle. It's the measurement of the distance the point on the circle moves through a unit of time. Okay, so basically you have two things in your car. You have the tachometer, which measures angular velocity, and you got the speedometer, which measures linear velocity. Now technically what the speedometer does, and I don't really know the engineering behind what the speedometer is doing. I've always assumed I know what it's doing. It's basically measuring how far a point on your tire is moving in a unit of time. That's what it's doing. So that point on that tire may go like 10 miles in an hour or something like that. That's what it's measuring, is that point on the outer edge of the tire, how far it goes in a unit of time. So that's what that's doing. So in velocity, the formula for, and this should say linear, you need to change that. That is, the formula for linear velocity is v equals s over t. Okay? So s is the arc length. That's the distance the point on the circle moves through a unit of time. T is the unit is time. Now the linear velocity units are going to be, I'll give you some, it's basically just a distance over a time. So it would be the same thing as your speedometer. It might be meters per second. Okay, it might be miles per hour is the common thing in this part of the world anyway. Okay, so miles per hour. That's what the speedometer is measuring. Okay, so that's kind of the idea. So I'll show you what we do with this formula v equals s over t in just a minute. But that's what angular or linear velocity is. Okay, all right. So let me go back to this Ferris wheel for a second, okay, and talk about this a little bit. So what we were talking about was the angular velocity is always the same no matter where you sit, okay? Like if you were a kid and on a merry-go-round. If you're on a merry-go-round, it wouldn't matter where you sat on that merry-go-round. You would still be going the same rotation in the same unit of time. But that thing right there and that thing right there have different linear speeds. Okay, which one goes the furthest distance? The one way out there or the one out in close? That one's going to go a further distance, right? So what it's going to have is it's going to have a faster linear velocity. Okay, if you think about that. Okay, here's another way to think about it. If you have a fan, like a plastic fan, and you can, I think about this when I teach it. If you stuck your finger at the very edge of that fan, it would hurt a lot more than it would if you put it right in the center, because it's going a lot faster way out there at the end. Okay, it's faster there. And then actually, if you look at a fan just like real close to the center, it doesn't look like it's turning very fast at all, because it isn't. Okay, so the idea is the linear velocity is different on that Ferris wheel, depending on where you are. Okay, that's something that you want to try to wrap your head around. Okay, so let me go through this. We're going to look at relating angular and linear velocity together here and just kind of wrap this up now. So we have a formula, v equals r omega. V is the linear velocity, r is the radius, and omega is the angular velocity. The formula you're going to use most of the time is looking at the relationship between these two things. Okay, so v equals radius times omega. Okay, that's how they connect. So let's see, I'll show you where the derivation of this comes from on the next page. It's pretty simple to derive this formula. So the idea is we're going to start like this. Let's start by writing down the formula. V is equal to s over t. Okay, now that's what linear velocity is. It's the arc, it's the distance that a point on a circle travels in a unit of time. So it's an arc over a unit of time. Well, the other thing is we know that s is r theta. That's the arc length formula we worked on a little bit earlier. So you want to replace s with r theta like that. Okay. Well, the next thing I'm going to do is we're going to kind of group this like this. That's really r times theta over t. But theta over t is omega. Okay, because that's what an angular velocity is, the angle something rotates in a unit of time. Therefore, you get r omega. So therefore, you end up getting the velocity, linear velocity is r times angular velocity, like that. That's where the formula goes from. You don't have to know the derivation, but it is good to get a sense of where all this stuff comes from. Okay, that's just mathematical manipulations is how we discover this stuff. Okay, so I'm going to do just a few more examples on this, kind of putting this together. I think in pre-calc, we don't go through this as much in depth as you do like a regular trig class. We do some harder examples. We just kind of do an overview in this class. So what this problem is saying is you have a truck with a 28-inch diameter. The wheels are traveling at 55 miles per hour. We're going to find the angular velocity of the wheels in radians per second. Okay. Now, most of you are going to be taking physics and stuff, and physics is the thing that students have trouble with a lot of times is not going through a good thought process. The good thought process to go through is write down what you're given, write down what you're trying to find, and write down whatever formulas are going to get you there. In physics, a lot of times there is multiple steps to go from A to B with thought processes and concepts and everything. So we're going to write down what we're given in this problem. What you're given is you have the diameter of the wheel is 28 inches. Now, we need to know the radius. Okay, so what's the radius? How does the radius compare to the diameter from your background? That's half of that, right? So the radius, R, is 14 inches. So you would have to know that basic fact, okay? Now, the next thing, and this is the whole key to doing these problems. This is what students mess up on these problems, is they don't know what they're given. Okay, 55 miles per hour. Is that a linear velocity or an angular velocity? It's linear. Why? Because the units, okay? If it was radians per second, then it would be an angular velocity. So that means that what we would have is V equals 55 miles per hour. Okay, that's what you're given, okay? Now, so we got that. I always kind of tell students, just write down what you're given. Now write down what you're trying to find. Well, what we're trying to find is we're trying to find the angular velocity. So we're trying to find omega in radians per second. Okay, so that's what we're trying to do. So here's the idea. You've only learned three formulas, only three formulas. You have V is S over T. You have omega is theta over T. And then you have V is equal to R omega. Well, in this particular problem, you know R. Okay, so we know that. We also know V. Okay, so that's the formula you're going to use because we got just one unknown left over in that problem. So now you got to know what formula to use. So third step is we have V is equal to R omega. Okay, so we're going to find omega. So what we can do on this is just divide both sides by R. So we get omega is equal to V over R. Okay, so we're going to do that. All right. So we're going to put that together now. So we just do omega. The angular velocity or the linear velocity is 55 miles per hour. Okay, let's see, the radius is 14 inches. Now the rest of this problem is unit conversion stuff. And there's a lot of it in this problem. Okay, a couple of things happening is the distances have to match up. You have miles and inches. You got to decide what you want to convert it to. You can either convert it both to miles or both to inches. It's your call. It doesn't make any difference, okay? So you're going to have to do unit conversions on this. Now, what I usually like to tell students to do in problems like this is just go through and do all your rounding at the very end of the problem. So this is what I'm going to do on this. I'm going to just kind of rewrite this like here. All right, so I think what I'm going to do is change miles to inches. I'll get a gigantic number, but that's okay. There's not a thing wrong with that. So when we do this dimensionally, what we're going to do is this, okay? I have no idea how many inches in a mile. I don't think you know either. But I do know there's 5,280 feet in a mile because I live in the mile-high city, right? So what I'm going to do is I'm going to say 5,280 miles make 1 foot, okay? And not everybody knows that, particularly international students. A lot of times they don't even know much about miles. And did I do something wrong? I did it wrong. I said it right, but I wrote it wrong, didn't I? Thank you, okay? 1 foot? That's a pretty big foot. Yeah, okay, so there's, hold on. I did do that wrong. Yeah, I got the numbers backwards too, okay? Sorry about that. Okay, so you're trying to get miles to go away and you're trying to end up with feet. That's the idea. So we know that there's 5,280 feet in 1 mile. Now I'm good. Okay, all right. And then the thing is we need to get to inches. Okay, so I need the feet to go away and I need to end up with inches. So on this it would be 1 foot is the same as 12 inches. Okay, so now I've got the inches put together like this then. So what I've got is you can cancel these units out. See, the inches cancel out now. One's on top, one's on bottom. Okay? And you can do this in a couple of steps. What I'm going to do is just do this on the calculator now. And we still got another thing that we're going to need to do on this. So I'm just going to do this. And you can just do this in one step. So I'm going to go 55 times 5280. And then times 12 in the numerator. And I'm just going to write that down for now. It's a big number, but that's okay. 3484800. And then I've got over 14. And then I've got, right now I'm in, what am I missing here? Did I cancel something else out? Oh, I'm in hours. Okay, I've got hours on this. So where I am is technically I just have a unit of hours. Now we're going to go to radians per unit of time. Notice that radians doesn't pop up in the formula. That's why I said a minute ago, radians is not technically a unit, it's a placeholder. Okay, because what's left over after all this cancellation, the only thing that I was left with was per hour. And technically angular velocity is just a number per time. Okay, like that. Now I got to do one more thing, so I got to change this to radians per second. Okay, so going to get the hours to go away. So I do this, okay, so, and we're going to go, and you can do this in one step if you want to, or 2 steps. So there is 60 minutes in 1 hour, and then we can make the minutes go away and end up with seconds. So the idea with this is in 1 minute there are 60 seconds, like that. Okay, so now we're where we need to be. We have radians per second, and we just need to do that arithmetic. Okay, and I'll go ahead and do this. You can do this calculation stuff in one step on your calculator, but I'm going to go ahead and just write this down. Students usually do a little bit better if they take the time to do a few steps. So I have 3,484,800 radians, and then I'll just do 14 times 60 times 60. I'll just square the 60 like that, and then that'll give 50,400. I'm left with seconds. Now I can just divide those two numbers. So I've got 3,484,800. And then I'm going to divide that by 50,400. All right, and that will give an answer of about 69, I'll just use 1 decimal, radians per second. Okay, so that's the answer to that problem. Okay, most of that problem was unit conversion, and that's what you'll find when you're doing these problems, is what you'll find in physics and chemistry and science classes, is you do all kinds of things with unit conversions. Yes? What's that? Oh, there's a second part of this. So we want to find the angular velocity in radians per second. Okay, so the other thing I want to do, I probably didn't give you guys a lot of room on your paper, so you can just kind of write down what you have room to do. So we got that. Now what we need to do is 69.1 radians per second. We're going to convert that to revolutions per minute. Okay, so if we do this, it goes like this. Okay, I don't want radians anymore. I want revolutions. Okay, what did I say a minute ago the connection between radians and revolutions was? 1 revolution is how many radians? 2 pi. Good. Okay, so 1 revolution, 2 pi. Okay, so we're now in radians per second. We want to go to revolutions per second. So now we want to get rid of the seconds, and we want to change that to minutes. Okay, and we know on that 60 seconds make 1 minute. Okay, so really all I'd have to do on this, I'm just going to do this in one step on the calculator. And this is a place where students mess up all the time, and you can't do stuff like this, especially if you're going to be like in engineering or any science. You got to know how to calculate. So what you got to do is you got to do 69.1 times 60 and get that. Now when you divide this by 2 pi, you've got to go like this. You've got to go parentheses 2 pi. I mean, you pay attention to stuff like that when you're doing your homework. You have to do, the calculator has to get 2 pi before it divides. So this would end up giving you about 659.9 revolutions per minute. Okay, so that means that truck is, the tire, every time a minute goes by, it's going through about 660 revolutions. That's what that means. Okay, so notice on that problem, most of what we did in that problem was unit conversion stuff. That's it. Okay. All right, everybody with me? Okay, maybe. Okay. We don't do any real difficult problems in this class, just because in pre-calc we kind of do an overview on certain things. So I'm going to go ahead and finish these next two up, then we'll take a break. So this example 4 says, find the distance along the arc of the surface of the Earth that subtends a central angle of 10 minutes, and then I'm giving you the radius of the Earth is 3,960 miles. Okay, so we're going to find the distance. Now this problem right here doesn't have anything to do with angular and linear velocity. Okay, I probably should have put this earlier in the notes. So we're going to find the distance of an arc. Now let's just write a little diagram on this. So here's Earth. Let's see the radius, and I think this is a fairly accurate radius. What you're given in this problem is you're given the radius of the Earth is 3,960 miles. Okay. And let's see, the other thing that we're given is the central angle theta is 10 minutes or 1/60th of a degree. Okay, we talked about a minute being a 60th of a degree before. Okay, so what we're going to try to do on this is it says find the distance along the arc of the surface of the Earth that subtends this angle. Now this is not drawn to scale, but what you're going to have is that angle is theta, and then that's S. Okay, so what we're trying to find is that, yeah.
Wouldn't theta be like 10/60ths or like 1/6?
I can't hear you, I'm sorry.
Wouldn't theta be like 1/6 instead of 1/60 since it's 10 minutes?
It is going to be. I'm not there yet, okay? 1/60th is 1 minute, so yeah, we're going to have to multiply that by 10, okay? Yeah, so let's do that now. So just multiply that by 10, so you would end up getting theta is 10/60ths, or that would be 1/6 of a degree. Okay, 1/6, okay, because it's 10 minutes, okay, it's not one minute. All right, everybody with me there? Okay. All right, so actually all we're doing is just finding the distance between these 2 points on the surface of the Earth. So that's what we're given. What we're going to find is we're going to find S. So we're going to use the formula S equals R theta. Okay, so we got to do that. All right, we know the radius, so we got that taken care of. We know theta. What do I need to do with theta, though? I got to change it to radians, otherwise I'm going to get nonsense answer on this problem, okay? All right, so we need to go ahead and do that. So before we put this together, we'll do theta is 1/6 of a degree. You multiply that by pi over 180, okay, like that, to change that to radians, okay, and you're just going to have a fraction. We're going to get a decimal answer on this problem anyway, so if I do 6 times 180, on my calculator, that will give me 1,080. So I basically have pi over 1,080 radians is what I have now, okay? Now to get my answer to the problem, I have the radius is 3,960 miles, okay? And then theta is pi over 1080 radians, okay? This will also help you understand that radians is unitless. There is no such thing as a radian mile. There's only such thing as a mile, okay? It's a placeholder, so just kind of ignore that. And then what we're going to do is we just do this on the calculator in one step. Then we've got an answer to the problem. So I'm going to just go 3,960 multiplied by pi, and then divide by 1080. You can divide, since you're dividing by just one number, you don't have to use parentheses around the 1080. So that would be about 11.2 I'll just round it like that, 11.5 miles. Okay? So now the next thing is, does that make sense to us? Okay? Well, 10 minutes is such a tiny angle that would mean the distance between these 2 points on the Earth, it would make sense to me that that's pretty small. How about you? Okay, so that's a tiny angle. All right, that's the idea with that. All right. Okay, so let's do one more here, and then that'll wrap up this part, and then I'll give you a break here. What we're doing on this problem is, example 5, it says you have a wheel that has a radius of 15 inches, and it's rotating at 20 degrees per second. Okay, so again, let's kind of take the same approach. Let's write down what we're given. We're given the radius is 15 inches. Now, what is 20 degrees per second? Is that linear velocity or angular velocity? That's angular. It's not in the units we expect, but we would have angular velocity is an angle per unit of time. So that's 20 degrees per second. That's why I know that it's omega. Okay, I already know that. So I've already given you the angular velocity. All I do on part A is just do a conversion, okay, to revolutions per minute. Okay, so what I'm going to do is we have omega is 20 degrees per second, and we're going to change this to revolutions per minute. Well, the first thing that you want to do on this is you want the degrees to go to radians. Okay, you got to do that. So what we're going to do is we're going to convert the 20 degrees, we're going to multiply by pi over 180. Okay, like that. That's going to basically just take this to radians then. Okay, then the other thing that we're going to have is, and I'm going to write that as pi over 180 radians because that's just kind of a placeholder. Okay, it's basically 180 degrees is the same thing as pi radians. So technically the degrees are a unit and they cancel out. Okay, that's how you can think of that. So right now I'm in radians and we need to go to revolutions per minute. So we've already done this several times. If I want radians to go away and become revolutions, we know that 1 revolution is the same thing as 2 pi radians. So now the radians are gone. Now I want the seconds to go away. So I put seconds on top and I want to end up with minutes. And we know that there's 60 seconds in 1 minute. Okay, so when you take all these units away, what I'm left with pretty clearly is revolutions per minute now. And the rest of this I can just do on the calculator. Now this one I'm going to do in one step. This is the safest way to do this. I see students do a lot of times beautiful job on this unit conversion. They get down to the end of it and put stuff wrong in their calculator. The safe way to always do this is always have your numerator in a set of parentheses. Even if you don't have to have it, it's safe to do it. So I'm going to do 20 pi times 60, close the parentheses, and then I'm going to put the denominator in parentheses. If you do it that way, you will never go wrong. So now I've got 180 in the bottom times 2 pi, like that, close the parentheses. Whoops, that's not what I meant to do. I hate it when that happens. Here we go. Okay, so now I got 2 pi like that. So I just got the numerator, 20 times pi times 60, denominator, I think I got everything right. Now I'm good. So let's see what we get here. So that is about 3.3, just round that off, 3.3 revolutions per minute is what that answer is going to be then. Okay, that's how that goes. Okay. So see, mostly what you're getting into is lots and lots of unit conversions, all right? Okay, next thing we got is what is the linear velocity. So if we want to find the linear velocity, we can just use r omega because we now know both things. So the radius in this problem was 15 inches, okay? Notice that the radius had nothing to do with the last problem. It doesn't. It has to do with linear velocity. So that's 15 inches. Now, the angular velocity, you don't want to use revolutions per minute. You want to use the radians. So what I'm going to do is take the 20 degrees per second, and again, I'm going to multiply that by pi over 180 so that that puts that in radians as my unit. Okay, see, really the degrees cancel out, so I've got that. Now, we want this to be in miles per hour. Okay, so we need to do that. So actually, we just got 2 things we got. We got to convert inches and seconds to miles per hour, and we're good. Okay? All right, so everything else I'm going to do is just work on the units. Okay, so again, inches on top inches needs to be on bottom. I know that there are, in this, I know basically like this, I know that there's 12 inches in 1 foot. Okay, so now the inches go away. I know that in, if I want feet to go away and end up with miles, I know 1 mile is 5,280 feet. So now I've got miles, and then I need the seconds to go to hours. Okay, so the seconds is on bottom, I put seconds on top, I want to end up with hours. So 1 hour is 60 seconds, and then that's the chain of events that you got to go through. Did I do something wrong again?
Seconds? 60 seconds in an hour?
Oh, in a, no, teacher. That's a pretty fast hour, isn't it? Yeah, so this goes like this. Okay, so what we have here is we have a second, and we wanted to end up with, and you can go this way if you want to. If you want to save a step, there's 3,600 seconds in an hour. Okay, you can do that if you want to. That way you don't have to do it twice. Okay, and then we're ready to go through and calculate to get our final answer of that problem then. Okay, all right, so now everything cancels out. So notice that what we're left with is miles on top and hours. And again, that radian is not really technically a unit. So to me, the safe way to do this is like this. This is what you ought to do as a student. You just do the numerator. 15 times 20 times pi times 3,600. And see, just use parentheses, and you'll never go wrong if you do it that way. And then do the denominator in parentheses. So that's 180 times 12. And then times 5,280, and then close off the parentheses, and then we got it. Okay, so I think I got everything in the calculator right, so that is going to be about 0.297. I'll just round it to 3, and then that would be miles per hour. Okay, all right, that's pretty slow, but if you think about the original problem, it's saying that every time a second goes by, it just goes through a little angle, 20 degrees in a second. Okay, so it's going to have a small velocity. That's going pretty slow. All right. Okay, any questions about that? Okay, are most of you familiar with this unit stuff, like from taking chemistry or physics and stuff? Because a lot of times, sometimes students get in this class, they haven't taken chemistry or anything before, and that's where I learned how to do all this dimensional stuff, because they don't usually teach you how to convert units this way until later. I've always thought this is the best way to do units anyway, because it's visual and you can tell you're doing it the right way. All right, so let's go ahead and let's break here for about 10 minutes, and then we'll come back and we'll work on actually we